Hey everybody, this is not going to be about power so much as it is work. We're going to do power another day, next time we meet. So today is all about work because you got an inclined plane lab to do, to practice your work, and find the efficiency of that thing and how the height of that thing affects the efficiency. So that's what we're working on today is what's this work stuff all about? And what it is, it's about a transfer of energy. It's how you transfer energy from one thing to another because there's something called the law of conservation of energy. Energy is always there, always been there, always will be there, but we change it from one form to another by means of doing work. Okay, so you got to learn about what work is to understand how this energy changes from one form and how we get stuff done. All right, here it is, guys. Look. Ooh, that looked like a lot of work by that dude over there. Here he goes. Wow, he's lifting a lot there. So work is done when a force moves an object, but here's the thing, moves at a distance. But the key is it has to be in the same direction, okay? And if it's not in the same direction, you got to do some trig there to figure out how to get those two in the same directions. That's how you find the work. It's force times your displacement, okay? Now, if it's a variant force, it might take some calculus to figure out what the work is. But as long as you have a constant force, not a problem. And by the way, this thing, it looks like it weighs 500 newtons. Hence, the person needs to put constant force of 500 newtons upward to move that thing. So now to find the work this dude is doing, all we have to do is find out how far he's moving. So it's just your force times displacement. Force is a vector, displacement is a vector. They have to be in the same direction. They can actually be in exactly the opposite direction as well. That's called negative work. Okay, that's how you lose energies, by doing negative work, or when the force is in the opposite direction of the displacement. But other than being exactly opposite, they have to be in the same direction, or there's a little trig you're going to do on here to make sure the displacement's in the direction of the force, or you're finding the component of the force in the direction of the displacement is really what you're doing. Oh, by the way, you have a special unit for this work and energy. It's a Newton times a meter in the metric system. So it's a Newton meter, which is a joule. After this guy Joule, we'll talk about another time that he did some things to find out mechanical energy can be turned into thermal energy. That's a story for another time. Alrighty, here it is, guys. Oh, there's the end of the mystery. That's one tall person. That's 2.5 meters that lifting that mass up. There you go. So 500 newtons pushing up times 2.5 meters. Well, that's not really that hard. It's 2.5 500s. That's 1250, guys. 1,250 joules. That seems like a lot of work right there. And not just once, but how many times is this person doing this work? Over and over and over. I don't know if it's going to be infinity here, but it looks like he's got a lot of lifts. And each single lift, the person is doing 1,250 joules. Now, here's the other part about it. So after one single lift, there is a certain amount of energy that thing has. Well, we'll get to that in just a minute. It's coming up in another slide. Okay? So how much work is done? By the way, that slowly lowers it downward. And and slowly lowering it. Okay. So, I don't know if I can pause the animation, but when you slowly lower the thing, well, you're actually lifting up. If you can imagine taking a bar and you're slowly lowering it, well, your forces are balanced, guys. If it's going down at a constant speed, forces are balanced. Sure, gravity's pulling down with 500, but you're pushing up with 500. And it's going down, that's negative work. That means we're actually losing energy. So that work that we just found a moment ago, let's go back to the work we just found a moment ago, the 1,250 joules. It turns out this dude has something to show for that, and it's called potential energy. Because when that thing is 2.5 meters higher, this thing now has 1,250 joules of potential energy. It means it's not doing anything at the top, but it can be. But as soon as this person lowers it, pulling upward with 500 or pushing up with 500 as it goes down in the opposite direction, 2.5 meters, now we're losing 1,250 joules. And hence there's no longer 1,250 joules of potential energy because we've lost it by negative work. Okay, another thing that gets a little complicated, so I don't like to get into it, but in reality, the dude is doing 1,250 joules of positive work to lift it up. but he's working against gravity. Gravity is a field force, always going to be conservative. We'll talk about that coming up in the next month, in fact. So being conservative means there's no energy loss, but gravity pulls down as it moves up. So technically gravity's doing negative work on it, but that's how we're storing it up into gravitational potential energy. Okay, you'll hear more about that later on. But as you slowly lower the thing down, that's a negative 500 because the opposite direction, it's losing 1,250 joules of potential energy, going all into nothing. It's sitting right back on the ground when you're all done. But if you're a lifter, that's part of the exercise, guys. It's not just the work to move it up. You're also getting a workout by lowering it down, not dropping it, because if you drop it, you're not doing any work. Okay, and that's what some people do, and it's annoying to everybody else in the whole gym. But when you slowly lower that thing down, you're actually giving your body quite the workout. Even though you're doing negative work, you're still getting quite a bit of exercise out of it. So the returning the weight back down at a constant speed is all part of the workout. So when the force is opposite displacement, it's called negative work. Alrighty. So there's no net work done. So if you do 1,250 joules up, negative 1,250 joules down, there's no net work done on it. In other words, when that barbell is back on the floor, it can't do anything more than it did before the thing was lifted. It's got no net energy change from right there. Oh, now it's got positive 1,250, and now it's going back down to zero again. There's no ability to do anything at the bottom, and none. So work is a way we keep track of energy. We're changing from one energy form to another. So where did that dude get the 1,250 joules of energy? From those muscles. How do those muscles get the energy? Food. Probably eats a lot of hot dogs, probably. And maybe he ate 1,250 joules of hot dogs, and that's how he got the energy. Where'd that energy from the hot dogs come from? Well, we've talked about that already. And talk about it again, we will. Hey, guys, how much work is this person doing there? Well, it seems like it's a little bit of work, but there's no net work going down because there's no change in motion. Sure, there's some potential energy. There's some work to put it up there, but there's actually no work happening. Even if the person is pushing up with 1,000 newtons, if it's not moving, there's no work done because there's no change in energy. If there's no change in energy, there's no work done. All change of energy happen because something's doing work. Work causes a change in energy. Alrighty, so there's no displacement, no work done. Okay, maybe some sweat pouring down and some work pushing the sweat out of the body. That's a different story. There's no work done on the weights. There could be work going on in here inside the person's body and everything because they're pumping blood around and getting exhausted. So work could be happening in the body, not on the weights. So if the weights don't move, there is no net work done on weights because there's no change in energy. Okay, so no work is done if there's no change in motion. Alrighty, guys, got some sample problems here. I know how much you love the sample problems, so these are 3 problems. We're just going to get to them individually, one by one. Here we go. Oops, I guess I jumped the gun on that one. I thought I skipped to number 1. Jill lifts a heavy object, weighs 100 Newton, 1 meter high. That's 100 times 1 meter. That's 100 joules of work. And she has 100 joules of potential energy to show for it as a result of doing that work. Now she lifts a heavy object with 5 kilograms, 1 meter high. Guys, kilograms is a mass. On planet Earth, pulls with 10 newtons for every kilogram. That means it weighs 50 newtons, so you have to apply 50 newtons over that 1 meter. That's 50 joules, right? Alrighty, guys, here it is. 100 newtons pushing on the A, 100 pushing on the B. Which has more work done it? Give you a moment, huh? You can pause and think about it. Is it the A or is it the B? Well, guys, remember, work is force times distance. So the work on the A1 is 100 times 5, or 500 joules of work done on it. This moves sideways at 5, but the sideways doesn't count. 5 meters sideways. What you have to do on the B is you have to find the component. There's the Y component of the force. There's the X component. So to find the work in the B, it's the F of X times 5 meters. Okay? They're both vectors. They have to be in the same direction. F of X is less than 100. So it turns out which of the boxes has the more work done on it? Well, that would be the A because the force is in the same direction as the displacement. So you have to do whatever you need to do to make sure the force is in the same direction of the displacement. All right, today's lab's all about inclined planes. So here we go, guys. Inclined planes is a way to make things easier. This dude, look at him sweating like crazy trying to move that up 1 meter. She's not having a problem in the world scooting that up 5 meters long this way. Still going to be 1 meter high, just like this person, if the person gets it there. So the reason you use inclined planes is it makes it easier. We'll find out in this case it makes it 5 times easier, but you can't get something for nothing. Okay? Sure, it might be over 5 times the distance. Well, ideally that would make it 1/5 the force to do that. And we're going to find out ideally it'd be the same work. Okay? So inclined plane, you're applying a force, but because it's over a longer distance, it takes less force. It's not any more or less work, ideally. Okay? So here we go. So Jill pushes this box up, 10-meter ramp, but it goes 2 meters high. The box will be 500. Ideally, how hard should you have to push? If she's pushing over 5 times the distance, I would expect, if they're in an ideal situation, 5 times the distance means 1/5 the force. It should be easier. So 1/5 the force would be 100 newtons. Or you could do it this long, hard way. That whatever work she puts in, which is her force times her distance, we're going to talk about that in a little bit, is the same as the output work, which is 500 times 2 meters. So the outcome is, without the ramp, you push straight up 500 newtons times 2 meters. Well, 500 times 2 meters is 1,000. And she's pushing some force times 10 meters. So we solve for that force. Well, it's 100 newtons. Because it's still 1,000 joules of potential energy when you push this 500 newtons straight up 2 meters. So it doesn't matter if you go straight up or this way, it's still 1,000 joules of potential energy. So ideally, 5 times the distance is 1/5 the force, ideally. In real life, that doesn't happen, guys. We don't have any ideal situations here, and you'll see in your inclined plane, even though it's virtual, you'll see that coming up shortly. Because no machine is 100% efficient, meaning you never get everything out than what you put in. In our fake case, ideal, that if you get out 1,000 joules, you'd only have to put in 1,000 joules. You're going to find out that's not true. You're going to have to put in more than what you get out. That's called life. You always got to put more work in what you get out. Otherwise, you're breaking the law. Not my law, the laws of physics, the law of nature. So whenever you do work, you're never going to get out what you put in. Get used to it. We try to be as efficient as we can, get as much out as we can, but it can't be 100% efficient. It goes against our laws of thermodynamics and nature. Okay? Alrighty. So here's real life. Jill is pushing a box up a ramp using 200 newtons over a 10-meter long plank. Guys, how much work is that? That is 200 newtons times 10 meters. That is 2,000 joules of work. But there it is. 500 newtons times 2 meters. That's the input. That's what Jill's doing. In real life, whoops, that's not real life. I got that backwards. We're doing the output. Guys, output is without the ramp. Without the ramp, it takes 500 newtons to lift straight up there. You might say, if it only takes 500 newtons, why not just lift it straight up there? We can't all lift 500 newtons easily, especially a big, cumbersome thing like that. So that's sometimes why we use an inclined plane like that. So without the ramp to lift it 2 meters, 500 times 2 is 1,000 joules. That's the potential energy it now has, or the potential to do work on something else. Now, in real life, she's pushing with 200 times 10 meters. Okay? So that's her input, what she's using the system. So in reality, she's using 2,000 joules to work in. She's doubling the work. Why in the world would anybody do this? It takes twice the work to use the ramp. Well, the reason you use the ramp is, even though it takes twice the work, that's less than half the force you have to use. It's pretty tricky to lift a 500 Newton big box like that. Not as tricky to push it with 200 Newtons. So even though you're doing more work, it's a little easier to get that thing up there. So to find the efficiencies, what you get out to what you put in, is 50%. Meaning 50% of the work she put in went into potential energy or stored energy. The other 50% was lost. And to what, you might ask?